In a world hungry for energy, we find ourselves at a crossroads. Traditional power sources, while reliable, contribute significantly to the concerning rise of greenhouse gases. The need for a cleaner, more efficient energy solution is critical. This leads us to the often misunderstood realm of nuclear power. Nuclear power, a force often shrouded in mystery and misconception, holds the potential to revolutionize our world's energy landscape. It's a form of energy generation that harnesses the immense power locked within atoms, specifically through a process called nuclear fission. Often perceived as a dangerous and volatile force, nuclear power in reality operates under stringent safety protocols, boasting an impressive track record. When we delve into its mechanics and understand the science behind it, we unveil a fascinating world of energy production with the potential to power our future sustainably. Join us on this journey as we demystify nuclear energy, exploring its principles, its benefits, and its crucial role in shaping a cleaner and more sustainable future. Welcome to Nuclear Power 101 Energy of the Future.
In an era marked by increasing environmental awareness, the quest for clean energy solutions has become paramount. Nuclear power emerges as a beacon of hope, offering a viable alternative to fossil fuels and their detrimental impact on our planet. Unlike its carbon-emitting counterparts, nuclear power plants generate electricity without releasing greenhouse gases into the atmosphere. This remarkable characteristic positions nuclear power as a key player in the fight against climate change, paving the way for a cleaner and more sustainable energy future. But the benefits of nuclear power extend beyond its environmental friendliness. Nuclear power plants boast an exceptional capacity factor, signifying their ability to operate continuously and reliably, providing a consistent and predictable energy supply. This reliability makes nuclear power a valuable asset in the global energy mix, ensuring energy security for nations worldwide. As we delve deeper into the intricacies of nuclear power, we'll uncover its potential to address the world's growing energy demands while minimizing our environmental footprint. Together, let's explore the transformative power of nuclear energy and its role in shaping a brighter future.
To truly grasp the immense power of nuclear energy, we must first journey into the heart of the atom. Atoms, the fundamental building blocks of all matter, consist of a dense nucleus at their core, orbited by tiny particles called electrons. The nucleus, although incredibly small, harbors the majority of an atom's mass. Within this nucleus reside protons, positively charged particles, and neutrons, particles with no charge. The number of protons determines an element's identity, while the number of neutrons can vary, giving rise to different isotopes of the same element. Certain isotopes, known as radioactive isotopes, possess unstable nuclei that undergo spontaneous transformations, releasing energy in the form of radiation. This inherent instability, while seemingly chaotic, forms the basis of nuclear energy. By harnessing the energy released during these nuclear transformations, specifically through a process called nuclear fission, we unlock a powerful and efficient source of energy with the potential to power our world. Nuclear fission, the process that fuels nuclear power plants, involves the splitting of a heavy atomic nucleus, typically uranium-235, into two or more lighter nuclei. This splitting is initiated by bombarding the nucleus with a neutron, a subatomic particle with no charge. When the neutron strikes the uranium nucleus, it disrupts the delicate balance of forces holding the nucleus together. This disruption causes the nucleus to become highly unstable, leading to its rapid and energetic fission into smaller fragments. During this fission process, a tremendous amount of energy is released in the form of heat and radiation. This energy originates from the conversion of a small fraction of the original mass of the uranium nucleus, as dictated by Einstein's famous equation, E = mc². The fission of a single uranium nucleus releases a relatively small amount of energy. However, the true power of nuclear fission lies in its ability to trigger a chain reaction, a self-sustaining process that amplifies the energy release exponentially.
Section 3. Controlling the chain reaction. The chain reaction, the heart of nuclear power generation, begins with the fission of a single uranium nucleus. This fission event releases neutrons, which can then go on to strike other uranium nuclei, triggering further fission events. Each fission event releases more neutrons, leading to a rapid and exponential increase in the number of fissions occurring within the reactor core. This self-sustaining chain reaction is the key to harnessing the immense energy potential of nuclear fission. However, this uncontrolled chain reaction can quickly escalate, leading to a dangerous and potentially catastrophic release of energy, as seen in nuclear weapons. To harness nuclear energy safely and efficiently, the chain reaction must be carefully controlled. This control is achieved through the use of control rods, typically made of materials like boron or cadmium, which have a high affinity for absorbing neutrons. By inserting or withdrawing these control rods into the reactor core, operators can regulate the number of neutrons available to sustain the chain reaction, ensuring it proceeds at a safe and controlled rate. Section 1. The reactor core, the heart of power generation. At the heart of every nuclear power plant lies the reactor core, a meticulously engineered structure where the magic of nuclear fission unfolds. Within this heavily shielded vessel, the controlled splitting of uranium atoms releases the immense energy that powers our homes and industries. The core houses an array of fuel rods, long, slender tubes meticulously filled with uranium pellets enriched to contain a higher concentration of the fissile isotope, uranium-235. These fuel rods, meticulously arranged within the core, serve as the primary source of nuclear fuel, their uranium atoms poised for fission. Interspersed among the fuel rods are control rods, crafted from materials like boron or cadmium, possessing a remarkable ability to absorb neutrons. These control rods, acting like the brakes of a car, regulate the rate of the nuclear chain reaction. By inserting or withdrawing these rods, operators can precisely control the number of neutrons available to sustain the fission process, ensuring it proceeds at a safe and steady pace. Surrounding the fuel and control rods is the moderator, typically water or graphite, playing a crucial role in slowing down the highly energetic neutrons released during fission. These slower neutrons, known as thermal neutrons, are more likely to interact with uranium nuclei, sustaining the chain reaction. The moderator, therefore, acts as a crucial intermediary, facilitating the continuous flow of energy within the reactor core. Section 2. From heat to electricity, the power conversion process. The immense heat generated within the reactor core, a testament to the power of nuclear fission, embarks on a journey of transformation, ultimately converting this raw energy into electricity. This conversion process, a marvel of engineering, begins with a critical component, the coolant. The coolant, typically water, or sometimes liquid metal or gas, circulates through the reactor core, absorbing the intense heat generated by nuclear fission. This heated coolant then travels to the steam generator, a massive heat exchanger where it transfers its thermal energy to a separate water loop, creating steam. This newly formed steam, now a carrier of the reactor's energy, surges towards the turbine, a colossal machine with rows of blades meticulously designed to capture the steam's kinetic energy. As the steam expands and rushes past the turbine blades, it sets the turbine spinning at an incredible speed. Connected to the spinning turbine is the generator, the final stage in this intricate energy conversion process. The generator, utilizing the fundamental principles of electromagnetism, converts the turbine's rotational energy into electricity. This electricity, now ready to power our world, flows through transmission lines, reaching our homes and industries, illuminating our lives.
Section 3. Shielding the atom safety and containment. The immense power of nuclear fission while holding the key to a sustainable energy future necessitates stringent safety measures to ensure the well-being of both people and the environment. Nuclear power plants therefore incorporate multiple layers of safety systems and robust containment structures to prevent the release of radiation. Encasing the reactor core is the containment structure, an imposing and impenetrable barrier designed to withstand extreme events, such as earthquakes, hurricanes, and even aircraft impacts. This robust structure, often made of thick layers of steel and concrete, acts as the last line of defense, preventing the escape of radioactive material in the unlikely event of an accident. Within the reactor itself, multiple safety systems work in harmony to prevent overheating and ensure the controlled operation of the nuclear chain reaction. Control rods, as previously mentioned, can be rapidly inserted into the core to halt the fission process, while emergency core cooling systems stand ready to flood the reactor with coolant should the need arise. Furthermore, nuclear power plants adhere to rigorous operating procedures and undergo regular inspections by regulatory bodies to ensure their safe and reliable operation. The nuclear industry prioritizes a safety-first culture, constantly striving to learn from past experiences and implement the highest standards of safety protocols.
Section 1. The workhorses, PWRs and BWRs. In the realm of nuclear power, two reactor designs have emerged as the workhorses of electricity generation: pressurized water reactors, or PWRs, and boiling water reactors, or BWRs. These two reactor types, while sharing the fundamental principles of nuclear fission, employ distinct approaches to harnessing the atom's energy. PWRs and BWRs represent the majority of operational nuclear power plants worldwide. Their proven track records and robust safety features solidifying their dominance in the nuclear energy landscape. Understanding the nuances of these reactor designs provides valuable insights into the complexities and advancements of nuclear power generation. PWRs, characterized by their use of high-pressure water as both coolant and moderator, prioritize safety and stability in their operation. BWRs, on the other hand, embrace a more direct approach, generating steam directly within the reactor core, simplifying the power conversion process. As we delve deeper into the intricacies of PWRs and BWRs, we'll uncover the engineering marvels that enable these reactors to safely and efficiently convert nuclear energy into electricity, powering our homes and industries. Section 2. PWRs, powering the present. Pressurized water reactors, the most prevalent type of nuclear reactor globally, stand as a testament to engineering ingenuity and a commitment to safety. These reactors, known for their robust design and reliable operation, have become the cornerstone of nuclear power generation in many countries. The defining characteristic of a PWR lies in its use of water under extremely high pressure, preventing it from boiling even at the elevated temperatures found within the reactor core. This pressurized water serves a dual purpose, acting as both a coolant, absorbing the intense heat generated by nuclear fission, and a moderator, slowing down neutrons to sustain the chain reaction. In a PWR, the heated coolant circulates through a closed primary loop, transferring its thermal energy to a separate secondary loop via a heat exchanger known as the steam generator. This separation of coolant loops ensures that the water used to generate steam, which ultimately drives the turbines, remains free of any radioactive material, enhancing safety and simplifying maintenance. PWRs, with their emphasis on safety and their proven track record, have earned the trust of many nations as a reliable and efficient source of electricity. Their robust design and stringent safety protocols make them a cornerstone of the global nuclear energy landscape. Boiling water reactors, or BWRs, the second most common type of nuclear reactor, take a more direct approach to harnessing the power of the atom. Unlike PWRs, which rely on a secondary loop to generate steam, BWRs produce steam directly within the reactor core, simplifying the power conversion process. In a BWR, water flowing through the reactor core absorbs heat from the nuclear fission process and reaches its boiling point, transforming into steam. This steam, now carrying the energy released from the atom, travels directly to the turbine, bypassing the need for a separate steam generator. While the direct steam generation in a BWR offers advantages in terms of simplicity and efficiency, it also presents unique challenges. The presence of radioactive steam in the turbine building necessitates additional safety measures and shielding to protect personnel and the environment. Despite these challenges, BWRs have proven to be a safe and reliable source of electricity, their distinct design offering advantages in certain applications. The continuous development and refinement of BWR technology further solidify their role in the diverse landscape of nuclear power generation.
As the world embraces the urgent need for cleaner energy solutions, the field of nuclear power is undergoing a renaissance, driven by the pursuit of even safer, more efficient, and more sustainable reactor designs. Advanced reactors, representing the cutting edge of nuclear technology, hold the promise of revolutionizing the way we harness the atom's energy. These next-generation reactors encompass a wide range of innovative concepts, each addressing specific challenges and pushing the boundaries of nuclear engineering. Small modular reactors, or SMRs for instance, prioritize scalability and flexibility, offering a more adaptable and potentially cost-effective alternative to traditional large-scale reactors. Fast breeder reactors, or FBRs, another promising avenue of advanced reactor development, possess the remarkable ability to generate more fissile material than they consume, offering the potential for a more sustainable and resource-efficient nuclear fuel cycle. Molten salt reactors, with their inherent safety features and their ability to operate at high temperatures, present intriguing possibilities for process heat applications and advanced fuel cycles. The development and deployment of advanced reactors represent a crucial step towards a cleaner and more sustainable energy future. These innovative designs, driven by a commitment to safety, efficiency, and sustainability, hold the key to unlocking the full potential of nuclear power in the 21st century and beyond.
In the realm of nuclear power, safety reigns supreme. The immense energy harnessed within a nuclear reactor demands an unwavering commitment to ensuring the well-being of both people and the environment. This commitment manifests in a multifaceted approach to safety, encompassing multiple layers of protection designed to prevent accidents and mitigate their potential consequences. Nuclear power plants stand as a testament to the philosophy of defense in depth, employing a symphony of safety systems working in harmony to prevent errors and ensure safe operation. Redundancy, a cornerstone of this approach, ensures that critical safety functions are backed up by multiple independent systems, minimizing the risk of a single point of failure. Diversity, another key principle, dictates that safety systems should employ different operating principles and technologies, further reducing the likelihood of a common cause failure. This multi-layered approach to safety, with its emphasis on redundancy, diversity, and a relentless pursuit of excellence, forms the bedrock of nuclear power's impressive safety record. From the meticulous design and construction of reactor components to the rigorous training and qualification of operating personnel, safety permeates every aspect of the nuclear power industry. This unwavering commitment to safety, coupled with a culture of continuous improvement, ensures that nuclear power plants operate safely and reliably, providing a vital source of clean energy for generations to come. Section 2. The Bastion Containment Structures. Imagine a fortress, its walls built to withstand the mightiest of forces, protecting what lies within from even the most extreme events. This is the essence of a nuclear power plant's containment structure, a testament to engineering ingenuity and an unwavering commitment to safety. The containment structure stands as the last line of defense, a formidable barrier designed to prevent the release of radioactive material in the highly unlikely event of an accident. Its construction is a marvel of engineering, often consisting of thick layers of steel and concrete, meticulously reinforced to withstand immense pressures, impacts, and seismic events. These structures undergo rigorous testing and analysis to ensure their ability to withstand a wide range of scenarios, from earthquakes and tornadoes to aircraft impacts and internal explosions. The containment structure's strength and resilience provide a vital layer of protection, safeguarding the surrounding environment and the public from harm. Inside the containment structure, multiple safety systems work in concert to prevent accidents and mitigate their potential consequences. Should an unexpected event occur, these systems are designed to shut down the reactor safely, preventing a release of radiation. The containment structure acts as a final safeguard, ensuring that even in the most extreme circumstances, the impact on the outside world remains minimal. Section 3. Emergency Response, ECSS and beyond. In the unlikely event of an abnormal situation within a nuclear reactor, a carefully orchestrated symphony of emergency response systems stands ready to swiftly and effectively mitigate any potential consequences. These systems, designed with multiple layers of redundancy and diversity, embody the nuclear industry's unwavering commitment to safety. Among the most critical of these systems is the Emergency Core Cooling System, ECCS, a sophisticated network of pumps, valves, and water sources, engineered to provide rapid cooling to the reactor core should the need arise. The ECCS acts as a safety net, ensuring that even in the event of a loss of normal cooling, the reactor core remains adequately cooled, preventing damage to the fuel and the potential release of radioactive material. Beyond the ECCS, nuclear power plants are equipped with a comprehensive array of emergency response systems, including backup power supplies, fire suppression systems, and sophisticated radiation monitoring networks. These systems, rigorously tested and maintained, provide an additional layer of assurance, ensuring the plant's ability to respond effectively to a wide range of potential events. Moreover, nuclear power plant operators undergo extensive training in emergency response procedures, honing their skills through regular drills and simulations. This rigorous training ensures that in the unlikely event of an emergency, the plant staff can respond swiftly, decisively, and effectively, minimizing any potential impact on the plant and the surrounding environment.
Section 1. The aftermath of fission: understanding nuclear waste. Nuclear power, while offering a clean and efficient energy source, generates a byproduct that demands careful attention and responsible management: nuclear waste. This waste, a consequence of the nuclear fission process, contains radioactive materials that emit radiation as they decay over time. Understanding the nature of nuclear waste is crucial for dispelling misconceptions and appreciating the comprehensive measures taken to ensure its safe handling and disposal. Nuclear waste is not a homogeneous mass, but rather exists in various forms, each with different levels of radioactivity and requiring specific management approaches. Low-level waste, comprising materials with relatively low radioactivity, typically originates from routine operations and maintenance activities. Intermediate-level waste, containing higher levels of radioactivity, includes resins, sludges, and reactor components. High-level waste, the most radioactive category, consists primarily of spent fuel rods, the remnants of the nuclear fuel after their energy-producing life within the reactor core. The safe and responsible management of nuclear waste is a paramount concern for the nuclear industry and regulatory bodies worldwide. Stringent regulations and comprehensive strategies are in place to ensure that nuclear waste is handled, transported, stored, and disposed of in a manner that protects human health and the environment for both present and future generations. Section 2. Safeguarding the future storage and disposal solutions. The safe and responsible management of nuclear waste, a byproduct of harnessing the atom's energy, presents both challenges and opportunities. The nuclear industry, driven by a commitment to protecting human health and the environment, has developed robust strategies for the safe storage and disposal of nuclear waste, ensuring its isolation from the biosphere for the duration of its radioactive decay. Short-term storage solutions, such as spent fuel pools, provide a secure and controlled environment for recently discharged fuel rods, allowing them to cool and their radioactivity to decay. These pools, typically located within the secure confines of nuclear power plants, are designed with robust shielding and cooling systems to ensure the safe containment of the spent fuel. For long-term storage and eventual disposal, dry cask storage and geological repositories represent the most viable options. Dry cask storage involves placing spent fuel rods in heavily shielded airtight containers that can be safely stored above ground for extended periods. These casks, designed to withstand extreme conditions, provide a high level of security and flexibility in waste management. Geological repositories, the ultimate destination for high-level waste, involve the deep underground burial of nuclear waste in stable geological formations. These repositories, meticulously selected and engineered, provide a permanent solution for isolating nuclear waste from the biosphere, ensuring its safe containment for thousands of years. The selection and development of geological repositories involve extensive scientific research, risk assessments, and public engagement to ensure the long-term safety and security of these facilities. Section 1. A clean energy paradigm. In the global pursuit of clean and sustainable energy sources, nuclear power emerges as a compelling contender, offering a unique combination of benefits that address some of the most pressing environmental challenges of our time. Unlike fossil fuel-based power generation, nuclear power plants produce electricity without releasing greenhouse gases into the atmosphere, making them a potent tool in the fight against climate change. The absence of carbon dioxide and other harmful emissions from nuclear power plants significantly reduces their impact on air quality and contributes to mitigating the adverse effects of climate change, such as global warming, extreme weather events, and rising sea levels. This characteristic positions nuclear power as a key player in the transition to a low-carbon energy future, enabling nations to meet their growing energy demands while reducing their environmental footprint. Moreover, nuclear power boasts a remarkably high energy density, meaning that a relatively small amount of fuel can generate a substantial amount of electricity. This inherent efficiency translates into a smaller land footprint compared to other renewable energy sources, such as solar and wind farms, which require vast areas to generate comparable amounts of power. Nuclear power plants, therefore, offer a land-efficient energy solution, minimizing the impact on ecosystems and land use. The environmental benefits of nuclear power, coupled with its reliability, scalability, and potential for technological advancements, make it a compelling option for nations seeking to decarbonize their energy sectors and ensure a sustainable energy future for generations to come. As the world grapples with the urgent need to address climate change and reduce our reliance on fossil fuels, nuclear power stands as a viable and potentially transformative energy source. Section 2. The Waste Management Challenge. While nuclear power offers a compelling solution to many environmental challenges, the issue of radioactive waste management remains a topic of ongoing discussion and a focal point for ensuring the long-term sustainability of this energy source. The radioactive byproducts generated during nuclear fission require careful handling, storage, and disposal to protect human health and the environment for both present and future generations. The nuclear industry, recognizing the paramount importance of responsible waste management, has developed robust strategies and technologies to address this challenge. Spent fuel pools, located at nuclear power plant sites, provide secure short-term storage for spent fuel assemblies, allowing them to cool and their radioactivity to decay. For long-term storage and eventual disposal, dry cask storage and geological repositories represent the most viable options. Dry cask storage involves placing spent fuel assemblies in heavily shielded, airtight containers that can be safely stored above ground for extended periods. These casks, designed to withstand extreme conditions, provide a high level of security and flexibility in waste management. Geological repositories, on the other hand, offer a permanent solution for isolating high-level radioactive waste from the biosphere. These repositories, meticulously selected and engineered, involve the deep underground burial of nuclear waste in stable geological formations. The selection and development of geological repositories involve extensive scientific research, risk assessments, and public engagement to ensure the long-term safety and security of these facilities. While the safe and responsible management of nuclear waste remains a complex and multifaceted challenge, the nuclear industry, in collaboration with regulatory bodies and scientific communities, continues to refine existing technologies and explore innovative solutions to ensure the sustainable use of nuclear power for generations to come. As the world navigates the complexities of climate change and the urgent need for clean energy solutions, the future of nuclear power hinges on a multifaceted approach that encompasses technological advancements, stringent safety protocols, robust waste management strategies, and transparent public engagement. The pursuit of a sustainable nuclear future demands a holistic perspective that addresses both the benefits and challenges associated with this powerful energy source. Advancements in nuclear technology, particularly the development of next-generation reactors, hold significant promise for enhancing safety, efficiency, and sustainability. Small modular reactors, with their smaller size, modular design, and enhanced safety features, offer greater flexibility in deployment and potentially lower capital costs. Fast breeder reactors, capable of generating more fuel than they consume, present intriguing possibilities for extending nuclear fuel resources and reducing waste generation. The continuous refinement of safety protocols, informed by lessons learned from past events and driven by a culture of continuous improvement, remains paramount for maintaining public trust and ensuring the safe operation of nuclear facilities. Transparent and open communication with the public, addressing concerns and providing accurate information about nuclear technology and its associated risks and benefits plays a crucial role in fostering informed decision-making and building public acceptance. A sustainable nuclear future necessitates a collaborative effort among governments, industry leaders, scientific communities, and the public to advance nuclear technology, strengthen safety measures, optimize waste management solutions, and engage in open and transparent dialogue. By embracing a balanced and comprehensive approach, nuclear power can play a significant role in shaping a cleaner, more sustainable, and energy-secure future for generations to come.
The pursuit of progress never ceases, and in the realm of nuclear energy, innovation continues to illuminate the path towards a cleaner, safer, and more sustainable energy future. Driven by the need to address climate change, enhance energy security, and minimize environmental impacts, researchers and engineers are exploring groundbreaking technologies that promise to revolutionize the way we harness the atom's power. Generation 4 reactors, representing the next evolutionary leap in nuclear technology, embody this spirit of innovation. These advanced reactor designs, still in various stages of development, aim to surpass the capabilities of existing reactors in terms of safety, efficiency, waste management, and proliferation resistance. Among the most promising Generation 4 concepts are small modular reactors, which offer enhanced safety features, scalability, and flexibility in deployment. Their smaller size and modular design allow for factory fabrication and transportation to site, potentially reducing construction costs and timelines. SMRs also offer greater flexibility in matching energy output to specific needs, making them suitable for a wider range of applications, including remote communities, industrial processes, and grid stabilization. Another groundbreaking avenue of innovation lies in fusion power, a technology that seeks to replicate the energy-producing processes occurring within the sun. Fusion involves fusing light atomic nuclei, such as those of hydrogen isotopes, to release immense amounts of energy. Unlike fission, which generates radioactive byproducts, fusion reactions produce minimal radioactive waste, primarily short-lived isotopes that decay relatively quickly. While fusion power remains a challenging technological endeavor, its potential for clean, safe, and nearly limitless energy continues to inspire research and development efforts worldwide. As the world grapples with the urgent need to decarbonize energy systems and mitigate the impacts of climate change, nuclear power is experiencing a resurgence of interest and investment on a global scale. Nations around the world are recognizing the unique benefits of nuclear energy, particularly its ability to provide reliable, baseload electricity without greenhouse gas emissions, making it a key component of a sustainable energy future. China, a nation rapidly expanding its energy infrastructure, has emerged as a global leader in nuclear power development, with ambitious plans to significantly increase its nuclear capacity in the coming decades. India, facing a similar surge in energy demand, is also pursuing an aggressive nuclear expansion program, aiming to enhance energy security and reduce its reliance on fossil fuels. In Europe, while some countries are phasing out nuclear power, others are recognizing its value in ensuring energy security and meeting climate goals. France, a long-standing proponent of nuclear energy, continues to rely heavily on nuclear power for its electricity generation, while countries like Finland and the United Kingdom are investing in new nuclear projects to enhance energy independence and reduce carbon emissions. This global nuclear renaissance is driven by a confluence of factors, including the increasing urgency of climate change, the need for reliable and affordable energy sources, and advancements in nuclear technology that enhance safety, efficiency, and sustainability. As nations around the world chart their courses towards a cleaner and more sustainable energy future, nuclear power is poised to play an increasingly vital role in meeting global energy demands while mitigating the impacts of climate change. Section 1. Success Stories. Powering Progress. The world of nuclear power, often perceived through the lens of cautionary tales, also boasts a rich tapestry of success stories. Power plants that have operated safely and reliably for decades, quietly powering progress and illuminating lives. These beacons of engineering excellence demonstrate the immense potential of nuclear energy when harnessed responsibly and efficiently. Nestled amidst the Arizona desert, the Palo Verde Nuclear Generating Station stands as a testament to the power of nuclear energy to provide clean, reliable electricity on a grand scale. As the largest nuclear power plant in the United States, Palo Verde's 3 reactors generate enough electricity to power over 4 million homes, making it a cornerstone of Arizona's energy portfolio and a shining example of safe and efficient nuclear operations. Across the globe, on the coast of Japan, the Kashiwazaki-Kariwa nuclear power plant, once the world's largest, stands as a symbol of resilience and technological prowess. Despite facing immense challenges, including a major earthquake and the Fukushima Daiichi accident, Kashiwazaki-Kariwa has undergone rigorous safety upgrades and resumed operations, reaffirming the potential for nuclear power to contribute to energy security even in seismically active regions. These success stories, along with countless others around the world, underscore the crucial role that nuclear power plays in meeting global energy demands while minimizing environmental impact. They serve as a testament to the dedication, ingenuity, and unwavering commitment to safety that characterize the nuclear industry, inspiring confidence in the potential for nuclear power to contribute to a cleaner, more sustainable energy future. Section 2. Learning from the past, accidents and advancements. The history of nuclear power, while marked by remarkable achievements, also bears the weight of accidents that have tested the industry's resilience and shaped its unwavering commitment to safety. These events, though tragic, have served as profound learning experiences, prompting rigorous investigations, technological advancements, and a global culture of continuous improvement in the pursuit of ever-safer nuclear operations. The Chernobyl disaster of 1986, the most severe nuclear accident in history, stands as a stark reminder of the devastating consequences that can arise from design flaws, operational errors, and a lack of transparency. The explosion and subsequent fire at the Chernobyl nuclear power plant in Ukraine released a significant amount of radioactive material into the atmosphere, resulting in widespread environmental contamination and long-term health impacts. The Fukushima Daiichi accident in 2011, triggered by a massive earthquake and tsunami, highlighted the importance of robust safety measures to withstand extreme natural events and the need for effective emergency response protocols. The meltdowns at 3 of the Fukushima reactors led to the release of radioactive material, prompting widespread evacuations and long-term efforts to decontaminate the affected areas. These accidents, while deeply unfortunate, have spurred significant advancements in nuclear safety culture, reactor design, and emergency preparedness. The lessons learned from Chernobyl and Fukushima have been integrated into international safety standards, regulatory frameworks, and industry best practices, ensuring that future generations can benefit from the advantages of nuclear power without repeating the mistakes of the past. The nuclear industry's unwavering commitment to learning from these events and continuously enhancing safety measures serves as a testament to its dedication to responsible and sustainable energy production. As we conclude our exploration of nuclear power, we find ourselves standing at the intersection of immense promise and persistent challenges. Nuclear energy, with its ability to generate vast amounts of electricity without emitting greenhouse gases, offers a compelling solution to some of the world's most pressing energy and environmental concerns. Yet the legacy of past accidents, the complexities of waste management, and the persistent fear surrounding radiation continue to fuel public apprehension and spark debate. The reality of nuclear power is a nuanced tapestry woven from both triumphs and tribulations. On one hand, we've witnessed the remarkable success of nuclear power plants operating safely and reliably for decades, providing clean, baseload electricity to millions of homes and industries worldwide. On the other hand, the shadows of Chernobyl and Fukushima serve as stark reminders of the potential consequences when safety protocols fail or unforeseen events overwhelm even the most robust defenses. The path forward for nuclear power hinges on a multifaceted approach grounded in technological innovation, unwavering commitment to safety, responsible waste management, and transparent public engagement. We must strive to develop and deploy even safer, more efficient, and more sustainable reactor designs, such as small modular reactors and Generation 4 concepts, while continuously refining safety protocols and learning from past experiences. Equally important is the need to address the complexities of nuclear waste management, exploring both existing solutions, such as dry cask storage and geological repositories, and innovative approaches that minimize waste generation and enhance long-term safety. Open and honest communication with the public, addressing concerns, dispelling myths, and fostering a balanced understanding of both the benefits and challenges of nuclear power is crucial for building trust and paving the way for a future where nuclear energy can play a vital role in meeting global energy demands sustainably. The future of energy is not about choosing a single path, but rather embracing a diverse portfolio of solutions tailored to specific needs and regional contexts. Nuclear power, with its unique attributes and its potential for technological advancement, deserves a prominent place in this energy mix, alongside renewable energy sources, energy efficiency measures, and smart grid technologies. As we venture further into the 21st century, driven by the urgency of climate change and the imperative for sustainable development, the role of nuclear power will continue to evolve. Innovations in reactor design, such as molten salt reactors and traveling wave reactors, hold the promise of enhanced safety, reduced waste generation, and even the potential to consume existing nuclear waste as fuel. The pursuit of fusion power, often dubbed the holy grail of energy production, continues to captivate the imaginations of scientists and engineers worldwide. Fusion, with its potential for clean, safe, and nearly limitless energy, represents a tantalizing glimpse into a future where humanity's energy needs are met without burdening the planet. The journey towards a sustainable energy future is a collective endeavor, requiring collaboration, innovation, and a shared commitment to safeguarding our planet for generations to come. Nuclear power, with its complexities, its challenges, and its immense potential, will undoubtedly play a significant role in shaping this future. By embracing a spirit of progress, guided by science, and driven by a shared vision of a cleaner, brighter future, we can harness the power of the atom responsibly and unlock its full potential to power a world where energy abundance and environmental sustainability go hand in hand.
We understand that nuclear power can be a complex and sometimes daunting topic, often surrounded by questions and concerns. In this segment, we aim to address some of the most frequently asked questions we've received from viewers like you, providing clear and concise answers based on scientific evidence and industry best practices. One common concern revolves around the safety of nuclear power plants, particularly in light of past accidents. While the events at Chernobyl and Fukushima were undoubtedly tragic, they served as catalysts for significant advancements in reactor design, safety protocols, and emergency preparedness. Modern nuclear power plants incorporate multiple layers of safety systems, robust containment structures, and rigorous regulatory oversight to minimize the risk of accidents and protect public health and the environment. Another frequently raised issue is the management of nuclear waste. While it's true that nuclear power generates radioactive byproducts, the volume of waste produced is relatively small compared to other industrial processes. Moreover, the nuclear industry has developed safe and secure methods for handling, storing, and disposing of nuclear waste, including spent fuel pools, dry cask storage, and geological repositories. These methods are designed to isolate radioactive waste from the biosphere for the duration of its hazardous lifetime, ensuring the protection of human health and the environment for both present and future generations. We encourage you to continue asking questions, seeking information, and engaging in informed discussions about nuclear power. By fostering a deeper understanding of this complex and potentially transformative energy source, we can collectively make informed decisions about our energy future. As we conclude our exploration of nuclear power, we want to emphasize that this is not the end of the conversation. It's just the beginning. Your voice, your questions, and your engagement are crucial in shaping a future where energy is abundant, sustainable, and accessible to all. We encourage you to share your thoughts and questions in the comments section below. What aspects of nuclear power intrigued you the most? What concerns do you still have? What role do you envision for nuclear energy in a future powered by progress? Our team of experts will be monitoring the comments and responding to your questions thoughtfully and informatively. We believe that open and transparent dialogue is essential for fostering understanding, addressing concerns, and building a shared vision for a brighter energy future. Thank you for joining us on this journey into the world of nuclear power. Together, let's continue the conversation, explore the possibilities, and work towards a future powered by progress, sustainability, and the promise of a cleaner, brighter world for generations to come.